Logs Lesson 1. Great unit to do on video because it's the best unit of the semester. You're going to like this one. And hopefully this video trial that we're doing is going to work well for you. You can take it home and pause, rewind, stop when you need to, and I think that is going to benefit everybody. So let's give it a shot. Lesson 1. We're going to start by graphing an exponential function. What is an exponential function? Pretty much what you would think, right? It has the exponent as your variable. So the variable is the exponent, it makes it an exponential function. But a couple other things that we need to keep in mind. A, just like with other functions, A is the vertical stretch, it's the coefficient in front. And in this case, we just say it's a constant, it can be anything. But there is a restriction with the base of the exponent. So C is the base of our exponent, and C is going to be only greater than 0. If C was equal to 0, then we would just have y equals 0 every time, because 0 to any exponent is equal to 0. So we want to look at the exponential changes, growth and decay, when C is positive values. If C was negative, then we get this flip-flop between positive and negative y values, which we don't want either. So we only are going to choose the base values that are greater than 0. A couple of common values for the base of the exponent is 2. If the base is 2, this is often considered to be a word problem that would be doubling in value. So you see any problems that are doubling have a base of 2. If you saw tripling in a word problem, then that would have a base of 3. There are some examples where you have a half-life of bacteria, or some examples that you've probably already seen in science. If you see half-life, that means the base is 1/2. And those are the 3 most common examples that you'll see. So let's graph. Let's graph a simple base 2 exponential function by taking a few values of x and determining what the y values would be. Don't need your calculators yet. So if we choose 0, so always easy value to choose, 2 to the power of 0 is 1. You have to remember a few of your laws of exponents. If you have a negative exponent, 2 to the negative 1 is equal to 1 over 2 to the power of 1. So remember, when you have a negative exponent, to take the reciprocal and make your exponent positive. So 1 over 2 to the positive 1 is just 1/2. 1 over 2 to the positive 2 is 1 over 4. And negative 3 exponent would be 1 over 8. Negative 4 would be 1 over 16. So we don't have a lot of space here, so let's choose a positive exponent, 2 to the power of 1, 2 to the power of 2. And now I want you to graph these points. Let's look at what this exponential curve is going to look like. 0, 1. Negative 1, 1/2. Negative 2, 1/4. Negative 3, and you can see the pattern here. It's getting harder to graph it because it's getting so close to the axes, but never touches. So if I go negative 7, it's half of that, negative 8, half of that. So it keeps getting smaller, but never equals 0. There's no exponent I can put into this equation that would equal 0. So we do have an asymptote happening here. It's approaching, but never touching. So on the positive exponent side, when x is 1, x is 2, 3 would be up at 8. And our graph then would look like this. Exponential growth. What is the domain here? I could have chosen any values of x that I wanted. X is real. Range is not real. Range is greater than, not equal to, 0. X-intercepts, where does it touch the x-axis? It doesn't. Now, this isn't always the case. If we have transformations happening, then we could move this graph down where it would have an x-intercept. But your basic y equals 2 to the x has no x-intercept. The y-intercept is at 1. That's going to happen no matter what the base is, because when you put a 0 as your exponent, it doesn't matter what the base is, that equals 1 every time. the asymptotes. We mentioned a minute ago. Y equals 0. It will never, that graph will never touch y equals 0. It approaches but never touches. All right, so that's our characteristic of y equals 2 to the x. How is that going to differ if we change our base to 1/2? Well, it's definitely going to differ. Let's try some values again. If I put a 0 in, doesn't matter what the base is, we get y value of 1. If I put a -1, now this is interesting. When I take the reciprocal of the base, now the reciprocal of 1/2 is 2 to the 1. A -2 is 2 to the positive 2 over 1, which is 4. So I'm going to take a positive x value of 1, 1/2 to the 1, 1/2 to the 2. And now what's this graph going to look like? Well, that same point, 0, 1, -1, 2, -2, 4. If I had -3, we would be at 8. Now this is where it decreases. So we have fraction 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, and so on. There it is. Okay. So I'll graph this and touch all these points. And let's go through these characteristics. You see what's going on here? I hope you can see why we call this exponential decay. It's decreasing and getting very, very, very small, but not getting to 0. So domain, we could have chosen anything for our exponent. Y is still greater than 0, not equal. X-intercept, same as before. Y-intercept, again, y equals 1. Asymptote, we do have our values approaching 0 but never touching. So y equals 0 is our horizontal asymptote. Okay, I'm going to go right on to the next page. And we are going to just do a quick discussion of what we just graphed. So exponential growth. You can see the first graph. The growth is very fast, and that's the nature of exponential growth. It starts slow, increases quickly. So there we go. That's exponential growth. It looks like it's touching the y-axis, the x-axis there where y is 0, but it is not actually touching. It's just getting very, very close. So it's increasing when the c value, remember the c is the base of the exponent, and if the c value is greater than 1, so the example that we did was 2, was 3, even if it's 1.5, as long as it's greater than 1, we will have exponential growth, so it's increasing. If you have a c value that's between 0 and 1, in other words, a fraction, but it has to be positive because we're still looking at values greater than 0, we're going to have the second graph, which is exponential decay. And this one, I'll write down growth, increasing, and decay is decreasing. All right, net decay is when you have a base that is a fraction. Oh, I just want to make sure that there isn't anything at the bottom here. These are base 3, so I didn't think they were any different than the graphs that we had graphed because of these points. Doesn't matter what the base is, but when you look at a few points on these specific graphs, if x is 1, y is 3, that gives it away right away that the base is 3. This point, -1, is 3, so that's an easy way to check what the base is. So just slightly different than our earlier graphs. All right, what if I gave you a graph and asked you to give me the equation? Look for a pattern in the ordered pairs. There's a couple of points here, 3 points actually, that are highlighted to help you decide what the base would be. Because 0, 1 doesn't help very much because all bases will give you a y value of 0 when the exponent will give you a y value of 1 when the exponent is 0. So 0, 1 isn't going to help much, but I guess 0, 1 will be this point. Negative 2, 25 is another point. Negative 1, 5. So if we look at a pattern here, just by looking at this point right here, negative 1, 5, negative 2, 25, we can see what the base of the exponent will be by looking at the x value of 1 or negative 1. That's the easiest way to tell. So if we have a base of 5, then an x value of negative 1 would be 1/5. But if I have a base of 1/5, then an x value that's negative will make the y value 5. And also I see that the graph is decreasing, so I know that the base has to be a fraction. And that fraction, when I raise it to a negative exponent, becomes a 5, 5 over 1, which is 5. And 1/5 to the negative 2 is the same as 5 over 1 squared, which is 25. So it looks as if our base must be 1/5. Y equals 1/5 to the power of x. Now I don't like the way this is written because it looks like 1 is raised to the power of x, not 1/5. So if we have a fraction as our base, it needs to be in brackets to indicate the whole fraction is raised to the power of x. All right, let's look at another example. So here's an example where it says the population triples every week, and it's modeled by the following exponential graph. So right away, if it triples every week, I know that the base of the exponent is 3. So let's say, what are the domain and range for this particular function? Well, I can see that the domain here is not real. It's time in weeks, so I can say x equals, or even better, t equals. T is time in weeks, greater than or equal to 0. If we're talking about time, be greater than or equal to 0. Range, in this case, range is the number of bacteria. So I'll say range is n. And we have a minimum here. We have a minimum number for the range. It's not 0, it's 1. So greater than or equal to 1 would be the range. Now write an exponential growth model that relates the number of bacteria to the time in weeks. So they're calling the number of bacteria b, so we can change our variable to b. And we're going to relate it to time in weeks. So I do have to do a quick check here. If the number of bacteria is b, then I know the base is t. The base is 3. And that is going to be t the time in weeks. The exponent this time is t, the x variable. And just to check to see if there is an a value, I can use the 0.13. So if this t value is 1, then the number of bacteria is 3. 3 to the 1 is 3. So I haven't stretched this. I haven't times it by anything. So that a value is 1. It's just b equals 3 to the power t. Determine approximately how many weeks it would take for the number of bacteria to increase to 21. So this says determine approximately. So the graph doesn't go up to 21. So let's just look at what that equation would look like. That would mean 21 is the number, 3 to the t. And we could just think about this. So what do you think approximately it would equal? So I know 3 to the 3 is 9. So it's bigger than 3. 3 to the power 4, 9 times another 3, is 27. Let's go rewind that for a second. 3 to the power of 2 is 9. 3 to the power of 3 is 27. So I know that t is between 2 and 3. So 21 is quite a bit larger than 9. So I feel that this value of the exponent would be closer to the 3 than the 2. So if I was going to estimate, I would likely say approximately 2.7. It would take approximately 2.7 weeks for the bacteria to reach 21. Now, to get a more accurate calculation, we could easily calculate this on our calculators and go y1 equals 3 to the x, y2 equals 21, change the window so y max is higher than 10, and graph. So I see my exponential curve that we have on our graph there. I see y2 at 21 horizontal line, second trace intersect, enter, 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 and I get 2.77, so I'm slightly off, but pretty close. So just to write down here what I did, I put y1 equals 3 to the x, y2 equals 21, and I did intersect, and I got x equals 2.77, so 2.8 weeks would be more accurate than what I have. But it did say determine approximately, so that 2.7 was pretty close, approximately. All right, let's look at how exponents and logs, or exponents for now, fit in with our transformations. Well, it's very much what you would think. The vertical stretch is the a value. So that a value is going to times, remember that 0.01, that's the point that's going to really make it obvious if we have a vertical stretch. If it doesn't go through the point A1, it means that we have some kind of transformation happening here. So if we have an a value of 4, that point now goes through the 0, 4. The y-intercept is now 4. And remember the reflection as well, because if a is less than 0, we don't get this exponential growth that we're used to seeing. It would be reflected on the x-axis. So this direction would be a negative a value. Reflection on the x-axis. All right, what about if we had a horizontal stretch? Horizontal stretches are a little harder to recognize because we would still have that 0.01. It would not change with a horizontal stretch. But if we have a base of 2, then we would definitely have different points happening here. A base of 2 means that that point that we're used to seeing, exponent 1, 2, that's your basic y equals 2 to the x. If we have, let's go to the red graph. If we have a b value of 3, that's a horizontal stretch of 1/3. So this x value of 1 now becomes 1/3. So the point 1/3, 2 is on the red graph because we have a horizontal stretch of 1/3. This would be 0.5. So b is 1/2, which means it's stretched by a factor of 2. But it's negative, so it's not stretched by a factor of 2 on the right side. It's on the left side. Okay, better use green here to match up with this graph. So this is the point that I would see reflected on the y-axis, but it's been stretched by a factor of 2. So this point moves to the point negative 2, 2. A reflection as well as a stretch. All right, what about vertical translation? So we're doing this a little bit in opposite order of SRT. Vertical and horizontal translations. So if we have h or k value, remember if it's vertical, it's being added on to the end. If it's horizontal, it's being added with the x value. So if you see an exponential function with a +2 over here, you know that that's vertical up 2. And you can see how the asymptote is affected with the k value. The asymptote at y equals 0 moves up to that k value. If you have a value, let's look at this, y equals 4 to the x is this one. This value is y equals 4 to the x down 3. So if you move a function down 3, that horizontal asymptote is now at -3. We haven't looked at the h value, so that was just vertical. But that's an important one because it affects the asymptote. If we move left or right, so left or right looks a little bit different because when you have an exponent that is your variable, you see the horizontal h value with the exponent. So if you see 6 to the power of x plus 2, we know the +2 means we're going left 2. So we take our original graph, y equals 6 to the power of x, and move it left 2. That key point is a nice one to show us that. If we have, in this case, we have 6 to the x minus 3, so this would be right 3, and we're going to move this point right 3 would be right there. So we're not changing the shape, we're just moving it left and right, and the horizontal asymptote doesn't change. The horizontal asymptote was just affected by the k value. All right, that covers our transformations. What if we were to look at a problem like this? Describe how each transformation changes. So replace x with x plus 2. We know that we replace x with an x minus 2. We're going to go to the right. Replace x with a negative x. Well, that's a negative x. That means it's a reflection over the y-axis. Y with a y minus 3. Remember, if you place y with y minus 3, that's on the left side of the equation. So that would be the same as moving the 3 to the right side and making it plus 3, which would move it up 3. Replacing y with a negative y, that would still be on the left side, but when you take the negative away from the left side, you times both sides by a negative, and that negative would be in front of the entire function, which means it's a reflection on the x-axis. Replacing x with a negative with a 5x. 5 is the b value, which is a horizontal stretch by 1/5. All right, last one. Replacing y with a 2y. So 2y would be on the left side. If we want to look at that as the a value, we would have to do the opposite operation, divide by 2, or when you're dividing by 2, that's the same as times by 1/2. So this would be a 1/2 in front of the entire function on the right, which is a vertical stretch by 1/2. Describe the transformations. Okay, so the a, in this case, what is the a value? This is a pretty complicated transformation here. We have a lot going on. The a value in this case is 1. It corresponds to a in the which axis. So let's see if they're talking about a reflection here. So sometimes we separate the reflection and the a value, but in this case we're talking about a reflection with the a value. So we're going to say a is -1 here. It corresponds to a reflection in the x-axis. So this negative right here would reflect it over the x-axis. The b value is 1/3, which is a horizontal stretch by a factor of 3. Now look at the h value here. Remember, the h value comes after the negative sign, and if that's a +2, that means it must have been a -2 h value to make it a +2. It corresponds to a horizontal translation of 2 units left. So that positive sign in the equation, we knew it was going to go left. K, in this case, I have to move this graph over a little bit, k is -1. And that corresponds to a vertical translation down 1. One unit down. this graph. So that is your basic graph. What is it going to look like if we do all of this to it? So if we do the horizontal, if we're going to graph this by hand, we would do the horizontal stretch first. So some good points, this would be invariant with a horizontal stretch. This would be a good one to stretch, that x value 1, 1, 2, we stretch it, times it by 3, and it becomes this. There's not very many that are right on, so that would be off the chart here. So I'm just going to start with those two. And then it's going to be a reflection on the x-axis. So that 0.34 is going to end up going down here. So kind of start to picture this as going through, this point is a -1 after we reflect it. So asymptote stays the same and it looks like this, but we're not finished yet. We have to go left 2, down 1. So now we still have the horizontal asymptote at 0, but when we go down 1, left 2, down 1, left 2, down 1, left 2. That horizontal asymptote has now moved down 1. So picture the horizontal asymptote here, and the graph going through these 2 points. And let's see if this will graph for us so we can check it out, what those points actually are going to look like. It's not going to graph for us. Oh, maybe not. So let's put in our calculators and check how accurate this looks with these transformations. It should be pretty accurate. Down 1, left 2, down 1, left 2, just to check these points after reflecting, down 1, left 2. I'm confident that that's correct. So the characteristics of this graph, domain would be real, range would be less than -1, less than -1. And the x-intercept is none. The y-intercept, I don't have an accurate look on my graph for the y-intercept, but I could calculate it by putting a 0 in here. So if we put a 0 here, this would be 1/3 to the 1/3 times 2, which is 2/3, 4 to the power of 2/3, and that would be negative, and then -1. So doing a quick calculation there. Let's do that. Y equals -4, 1/3, 0 plus 2, -1. That is going to give us our y-intercept. So I'm going to go 1/3 times 2, 4 to that exponent, and that's negative, so I'm going to times that by -1, and then I'm going to subtract 1, and I'm getting -3.5. So on this graph, -2, -3.5, well, that wasn't too far off of that y-intercept, so graph was a little bit more accurate than I was expecting, but that is a good calculation of your y-intercept. You can also put in your calculator and go second trace value, x is 0, to get the y-intercept. I just want to check at the bottom of this that didn't miss anything there. No. Exponential growth decay are also important parts of the exponential function. So here's a formula that's not on your formula sheet. This is the formula that's on your formula sheet. This is much more common, but it is really the same thing. Different variables. B is the base, so that's common. And B is the base, and that's where you're going to see a doubling time, tripling time, or half-life. That's going to determine the base. We often see the initial amount given. The initial amount is the coefficient, the A value, is the initial amount. So starting amount is the A value. And NT is the amount after a given time, after a given time that has elapsed. So this is the time elapsed. And that is the amount after a given time. Now D is the time it takes for the growth or decay to occur. And this is what I call the official doubling time or tripling time or half-life. Sometimes you're determining that and sometimes you're given that. The time it takes for the growth or decay to occur. So it'll make more sense when you see an example, I hope. Let's try one. Real estate board in a city announces that the current average price of a house is $400,000. So the current price, and that would be the starting amount. A would be the $400,000. And it will double. The word double right there tells us that this is 2, that our base is 2. It doubles every 15 years. So the big mistake people make here is whether to put 15 in for for T or P. In the last example we used D, but the denominator is the time it takes to double. So the 15 is the denominator. So if we put this together, it looks like this equation. Once you have an equation, we can answer many questions based on this equation. Describe how each of the parameters in the transformed relates to the information. All right, let's go through. A is 40,000, and that is, sorry, did I say 40? 400,000. That's the starting population or initial population. B value is 2, and that represents the doubling or the amount it's increasing. So it's increasing, it's doubling. So let's see, it says up here, real estate, its current average price, it predicts average prices will double. So doubling, okay, doubling is the amount of increase, I'll say. And P. P is a variable used in this example, and that represents the doubling time, and that's 15. We always need to check the units for P and T. So we're talking about 15, and going back to the original again, sorry for moving up and down, 15 years. So that is the time it takes to double. And that's in years. And we have to be careful that when we talk about time elapsed, that it is in the same units. So it says predict the value of a house after 10 years. When will the house be worth 50,000? Well, if we have an equation, so let's say our equation is this, T is the time elapsed over 15. Oh, pardon me, this is Y equals 400,000. Now, if I want to predict the house after 10 years, I'm going to put a 10 in for T and just put that in my calculator. So that's not a graphing question. I can just do that by calculating it on my calculator. So if I put this into my calculator, I'm going to go 400,000 times base 2 bracket exponent. I'm going to put my exponent in brackets. 10 over 15, and enter. So it takes 15 years to double, so I shouldn't see 800,000 after 10 years, but somewhere in between. So I'm getting this number, 6349.60 to the nearest dollar. And the second question, when will the house be worth 500,000? What I would do with that one is a Y1, Y2. Y1, Y2 question. So this would be definitely adjust your window and find the intersection of these. So here's what we would see. If we just graph the first one, we can get this calculation that I just calculated by going to 10 on the X. So if we go second trace value, X is 10, we get this same answer that I just calculated a moment ago. So that's if we know an X value. If we don't know an X value, like this example, we would graph y1, y2, and y2 is 500,000. This is your exponential graph with the 400,000 as your initial amount. This intersection point is going to tell us how long in years it will take to reach 500,000. It looks like just 5 years, just short of 5 years, so 4 point something there. So you put that in your calculator and get an exact value. Didn't say how to round it, but let's see, when will the house be worth? Okay, so you have the idea. When you're given a y value, it's y1, y2 intersect. If you're given an x value, you can just plug it in to your equation. Now we're going to have to stop here. You see that one example is the last one. And I will come back and put part 2 for your exponential functions. And I'm going to put these on D12 for you to access. And that is it for this lesson for now. So I'll finish it with a second add-on video.